Okay, for what we have in continuing with second order differential equations, and in terms of the sequence of the sections in the book, it might seem as if we are backpedaling, so to speak, but in a sense, we are continuing on with the topics of what we have covered with homogeneous and non homogeneous differential equations. And I want to look into special cases where, like in the case of homogeneous equations, we have had the characteristic root equation, and in the case of non-homogeneous equations, we have had utilized the method of undetermined coefficients. And there can be potentially those second order differential equations where we might not be able to utilize either method. And for this part, okay, and this is what we have in section 1.6, and we have for reducible second order differential equations. And again, a second order differential equation involves the second derivative of the unknown function y of x, and it's going to have this particular general form where we have f of x and y prime, and y double prime is equal to 0. And if we have either x or y to be missing from the second order equation, then we can reduce by substitution to a first order equation that might be solvable by methods that will be for what we have utilized in our techniques so far. And let's say that, okay, for this setup, if you happen to have the variable y to be missing, then this equation, okay, with y missing, okay, is going to be where we have f of x, y prime, and y double prime is equal to 0. And with what we have in reference to substitution, and we can say we have a variable p is equal to y prime is equal to dy over dx if we utilize Leibniz's notation. And if we take the derivative with respect to x of p, okay, so you have dp over dx, and that is simultaneously equal to the second order derivative of what we have in y with respect to x. So we have dp over dx is equal to p prime is equal to y double prime, which is equal to d squared y all over dx squared. And this particular equation is going to take on the form this time where we have f, again we have x, y prime becomes p, and y double prime, okay, we have to be at p prime, where we have that is equal to 0. And just for the general layout, okay, so we have y of x is equal to the integral of y prime of x dx, and in terms of what we have with the substitution variable p, so we're going to have the integral of p of x and the first constant dx followed by the addition of a second constant. And let's say as a case of what we have with the reducible second order differential equation, and this is going to be one where you could also use the method of undetermined coefficients because they have a homogeneous equation to be this type where we can establish complementary as well as a particular solution. But for the techniques that we have in the situation, so you have y double prime plus 2y prime is equal to 8x. And again, y double prime, you have d squared y over dx squared plus 2 times dy over dx is equal to 8x. And again, just going back to what we have in the substitution variable p. So again, p, we have it dy over dx. And again, p prime is going to be d squared y over dx squared. Okay, and p prime, we have dp over dx. And again, for 2y prime, that would become 2p. And so we have dp over dx plus 2p is equal to 8x. And if you notice, okay, we have linear first order equation in the substitution variable p. And again, so we have with the dependent variable with p and the independent variable with x. And we can use, once again, treating as a first order linear differential equation in the variable p. And so we have, just from the algorithm now, we have lowercase p in the substitution variable, but in accordance with the first order linear differential equation standard layout, we have an uppercase p. So these are not the same p. And we have for p of x, okay, that is equal to 2. And for q of x, that is equal to 8x. And in establishing the integrating factor row, we have equal to e to the integral of p of x dx, and that is equal to e to the integral of 2 dx. And so we end up with our integrating factor at e to the 2x. And if we take the integrating factor and multiply by the standard form of what we have in the substitution variable p, okay, so I have e to the 2x over the left-hand side is equal to 8x times e to the 2x. And so we have on the left-hand side, again, that is going to be taking the derivative in x of the product of the integrating factor e to the 2x times the dependent variable p. And again, we have is equal to 8x times e to the 2x. And integrating over both sides, okay, so you're going to have e to the 2x times p freed up from the parentheses. And for integrating over 8x e to the 2x, okay, we're looking at integration by parts. And, okay, so again, you have u times v minus the integral of v du, and drawing the coefficient 8 out, so you have u at x, and we have the differential du equal to the differential dx. And for the e to the 2x dx portion, to which we have dv set equal, antiderivative, we have 1/2 of e to the 2x. So we have in the pattern, so we have 8 times x times 1/2, which is going to be 4x e to the 2x. And then we have minus, okay, what's going to be 8 times v, which is 1/2 of e to the 2x, resulting in 4 e to the 2x, and you have times du, which we have at dx. And so we have 4x e to the 2x, and for the antiderivative of e to the 2x dx, we have again 1/2 of e to the 2x, and negative 4 times that lands at negative 2e to the 2x. So the result here, okay, is going to be that which we have the freed up e to the 2x p set equal. And isolating the variable p, we have division by e to the 2x, where we have 4x minus 2 plus c sub 1 e to the negative 2x. Okay, so for the expressions we have defining p, okay, so we can set equal to each other dy over dx, and 4x minus 2 plus c sub 1 e to the negative 2x. And if I separate the differentials and integrate, so dy leads to y, antiderivative 4x minus 2 plus c sub 1 e to the negative 2x. We have 2x squared minus 2x minus 1/2 of c sub 1 e to the negative 2x, followed by the second constant. And again, c sub 1 over 2, or the negative thereof, you can write in terms of adding a constant. Constant over a constant is a constant. So we can rewrite this as 2x squared minus 2x plus alpha e to the negative 2x. And you can say, like for c sub 2, you could either leave it as it is or throw in some other letter like b or beta or gamma. But anyway, this is going to be the general solution of what we have here. And again, this equation is one where, again, just going back to our technique from last week, again, you can arrive at complementary and particular solutions. And again, for the complementary solution of y double prime plus 2y prime is equal to 8x. Again, if I had this to be a homogeneous equation set equal to 0, we would have from the characteristic root equation with the roots at 0 and negative 2, I have the complementary as c sub 1 plus c sub 2 e raised to the negative 2x. And we have with 8x, again, if I look at breaking it down in terms of what we have in the variable expression and breaking it down in terms of the family of derivatives. So we have with 8x, again, we had the variable x, derivative goes to a constant. And if you notice, okay, we have with the constants, okay, there is a duplication. And anytime we have a duplication, we're looking at multiplying this set by a power of x. So x becomes x squared, and the constant, we just say that goes to constant times x, or just x itself. And with the use of the method of undetermined coefficients, we have y sub p equal to ax squared plus bx. And we're going to go out to the second order derivative. So the first order derivative, we have y sub p prime is equal to 2ax plus b. And the second order derivative has b to go out, and 2ax becomes 2a. And then substituting and putting this equation in terms of the particular So we have y sub p double primes at 2a, and you have 2 times the first order derivative of y sub p. And that's going to be 2 times the quantity of 2ax plus b, and we have is equal to 8x. And then just looking at what we have in the corresponding parts, we have 4ax and 8x will map together. So we have 4a is equal to 8 and a is equal to 2. And with just the constants, now we don't have a non-negligible constant alongside 8x, so we're going to have 0. And so for the left, we have the constant representations with 2a and 2b. And with a at 2, we're going to have 2 times 2 is 4, plus 2b is equal to 0. And we had that b is equal to negative 2. And looking at back substituting into the particulars, so we have a at 2 and b again at negative 2. So we're going to have y sub p is equal to 2x squared minus 2x. And including what we have with the complementary, so y sub x, or I should say y of x, is equal to 2x squared minus 2x plus c sub 1 plus c sub 2 times e to the negative 2x. And guess what? That is conceptually identical to what I have with this other methodology.